Hi, I'm going to be talking about Kafka Streams, challenges of stateful streams processing with local state stores, and present and assess an alternative implementation to persist state to Apache Cassandra or Scylla. My name is Hartmut Armbruster. I'm an indie software engineer, and over the past couple of years, I've been working with distributed systems and real-time data processing for various big clients. I'm passionate about efficient end-to-end architecture. On to today's agenda. Since this is Scylla Summit and not Kafka Summit, I'm going to do a quick recap on Kafka Streams State Stores and RocksDB. Moving on to challenges and opportunities managing state, and introduce a library Kafka Streams Cassandra-State Store. It's a drop-in state store alternative, so we'll show a quick start. We'll look at data models and supported store types, interactive queries, and wrap up with conclusions, limitations, and next steps. Let's get started. I'm sure many of the summit attendees know what Kafka is, but nevertheless, I will cover the fundamentals of Kafka Streams. I will have to be brief, so I will keep it as high level as possible and as low level as necessary. Apache Kafka is a distributed event streaming platform. Data is stored in topics, which are immutable and append only. Topics are further sharded into partitions, and events are key value pairs ordered and partitioned by key. Kafka Streams is a Java library to write applications to do stream processing on data stored in Kafka topics. The business logic is defined through a processor topology that makes up the data flow. There are three types of processors: source, stream, and sink. Sources and sinks are Kafka topics, while stream processors can be categorized into basic operations such as filter, map, flat map that are stateless in nature, and stateful ones such as join, group, window, or aggregate. Important for today's talk, stateful processors that store data in what is called state stores in Kafka Streams. Kafka Streams maintains its state local in RocksDB or in memory. For RocksDB, this local state is written to the file system, so it lives on disk where your application is running. Data or stores, as everything in Kafka, are also partitioned and therefore distributed across all running instances. Data is written to the local store and also to changelog topics. Changelog topics are internal Kafka topics, and they benefit from all of Kafka's architectured resilience with topic replication and failover. That allows for state to be restored when local state is lost or needs to move, providing full fault tolerance. A state restore essentially takes place when the streams application starts up with an empty state and there are records in the changelog topic. Only when the entire changelog has been consumed and backfilled into the local state stores, the application transitions into a running state and starts to consume from the source topics and process data. Kafka Streams is an excellent choice for streams processing. It's robust, performant, reliable, and widely used across all sorts of industries. So what challenges or problems can a new type of state store address? The concept of local state stores is extremely powerful, but it also has a few downsides. Let's take a closer look at two of them. The first example use case is simply real-time data processing with a considerably large state. This could be anything like a food delivery backend, transport, or banking application. Now, modern day software engineering, there's no ship once, keep on running. Obviously, once you go into production, you will continue working on your application and you will need to deploy upgrades and roll out new releases. You need to do security patching to fix CVEs on your application, like the container base image or the infrastructure itself, where the application is running on. Infrastructure also fails, where you need to recover, or you simply want to scale up or down your running application. In such scenarios, a state restore may be required and triggered. Delays are proportional to the number of records in a changelog topic and may take minutes or hours to complete, where both processing and interactive queries are paused. Now, with your real-time data processing as a requirement, this is a clear breach of your NFR and a no-go if everything kind of comes to a halt for multiple hours. There are many options to mitigate the impact, but there's no definite solution to the problem due to the very concept of local state. There's not enough time to elaborate and dive in, but feel free to speak to me after this talk. Here's a second example I've personally spent a lot of time analyzing, debugging, and trying to get on top of. Idle streams group members. In Kafka Streams, there's a concept called warm-up replicas. Warm-up replicas are standbys created on demand to smooth task reassignment by preloading state in the background. While they work most of the time, the primary drawback of warm-up replicas is that they complicate the assignment protocol and often leave the application unbalanced. This may happen for more complex streams applications with many input source topics, and where simply the transition from warm-up to active never happens. If you end up with an unbalanced assignment, this means idle replicas, performance degradation, and unused allocated resources that cost you money. So, having the groundwork laid out, let me introduce you to Kafka Streams Cassandra State Store. Let's start with the simplified architecture diagram from earlier of a stateful Kafka Streams application. Now, to modify for our state store, no surprise, we're going to replace the local state store with a Cassandra table. Simple as that. With the state persisted in an external database, there's no longer any need to restore state, so we can also drop the changelog topic that serves as our backup. Now, storing data in a database is nothing innovative. That's what we've been doing, well, since databases exist. So, has no one had this idea before? Why does no such solution exist? Of course, one of the reasons it's not as simple as it looks, and it's not all milk and honey. But let's first continue and keep the evaluation for last. Now, this design would fundamentally work with any database. So the question is why Cassandra or Scylla? Same as Kafka, Cassandra or Scylla is a distributed system. It scales well both for reads and writes and also for data volumes. It's highly available through data replication, same as Kafka. It's highly fault tolerant, comes with high performance, and as a bonus, it also allows expiring data with TTL. So, How to use this library? As a quick start, it's available on Maven Central. So simply add your dependency using Maven or Gradle. And in addition, also use a Java driver here, the Suda sharded driver fork of the DataStax one. Next, as an example, using the high-level DSL, here's the most basic example of defining a K table, a Kafka Streams high-level entity, through the streams builder .table and the topic name. If you do this by default, under the hood, RocksDB is used as a state store as the basis for your K table. Now, same as you would switch to an in-memory state store, the builder.table method is overloaded with passing in a materialized. And here within or under the materialized, we pass in Cassandra State Stores builder. We pass in the SQL session, the store name, and we choose our state store type. In this example, it's a partition key value store. Some details, please check the docs. One of them is you should, or it's recommended to disable logging, which means there will be no changelog topic created and backfilled. Looking at the builder, what was used in the previous slide is the most basic or only the mandatory fields of the builder, where you pass in the session this name and choose your type. But there are many more optional config options for your builder, such as setting the key space or execution profiles or table options. This is helpful if you want to override the default compaction strategy the table is created with, or set the default type to live. You can read all of the options in the documentation. Now, let's take a look under the hood at the data model used. Here's a create table statement showing how the table for a partition key value state store looks like. And it's actually pretty simple. We only have 4 columns: partition, key, value, and timestamp. What I want to highlight is that key and value are of type blob. So any payloads are supported. So you can use string, numbers, uprow, or protobuf, for example. Since everything is simply serialized as bytes, it's a total generic solution you can use just like the default state stores, RocksDB, or in-memory, without anything special or extra to do. No limitations. As an example, if you query this table, well, here it's also using blob as text. You can see all of the data written with partition, key, and well, the value is still serialized. A second detail I want to showcase is looking at the primary keys. Here the same create table definition for a partitioned type key value store, where our primary key is a composite key with using the key. So this is the key of your item put into the state store by Kafka Streams, which is a key value pair. This key is essentially also your Kafka or your Kafka Streams processing message key. Is also used as the clustering key in this table. This allows for additional interactive queries such as range scans and prefix scan. To mention here, important, the number of partitions is defined by the streams tasks, and this is defined by the source topic partitions. Since this is a fixed number, you can end up easily with large partitions, so it's not really made for large or high volumes of data. Another benefit on the other side is batch inserts are possible and efficient, since all data written within a streams task are always for a single partition where you can do a batch insert in one go. There's another type which is called global key value store provided. It's almost the same structure, just without that first column partition. So we have a single primary key on the column key. This ensures a high cardinality and works for any data volumes you might choose. On the other hand, there's no support for range or prefix scan, since it's simply not possible to query this primary key in any way to do such range scans. A benefit for this type is that lookups are possible from any instance without any knowledge or context of the partition or task required. This can be very useful for various use cases for interactive queries. We will get to that in a minute. To summarize, the library provides different store types with different traits due to some small but substantial differences in the underlying data models. Please make sure to read the documentation to make the right choice for your individual use case. Version key value state stores introduced to Kafka Streams with version 3.5 are also supported. Moving on to interactive queries. So interactive queries in Kafka Streams let you directly access and query the real-time state of your stream processing application. So it's a programming interface where you can do like get by key, or like mentioned earlier, like get all, do a range query, or a prefix scan based on your keys. Interactive queries, let's look at an example where we expose our state via a REST API. So on the right hand side you can see an HTTP client requesting round robin to our stream instances, and this will become easier with an external state store, since there's no need for RPC, so remote procedure calls, between the running instances. Let's take a closer look to understand how this works and why this is necessary. So for regular Kafka Streams State Stores, the state is partitioned and distributed across all application instances. In this example, there are 4 partitions in the topic, color-coded, each one assigned to one of the 3 instances, and so is also the state. To access data that's not in your local store, you need to call out to the correct assignee over the network. To do range queries or read all store entries, you even need to query all other instances via such a remote call. With Cassandra State Stores, on the other hand, all instances can access all data directly, since you just query the database. Same as with any old school stateless backend application. To take advantage of this, use the interface provided by the library to efficiently query data for any store type, the partitioned or also the global key value store. Okay, conclusions. So there are many benefits with choosing an external state store over the local state stores provided by default with Kafka Streams. This library is a drop-in replacement state store, so you don't need to rewrite your Streams application, just slightly modify to replace the existing used RocksDB state with the library's Kafka Cassandra State Store. It's a persistent and allows for very large state. And as mentioned before, there are no changelog topics involved, no state restores required. So you can simply run your stateful streams application as in a stateless fashion. It allows for instant rebalancing and therefore reduces the rebalance downtimes to bare minimum and also recovery times. Where you might have taken hours for a state restore before, it can now be done with a 100 millisecond rebalance. And this greatly improves elasticity and scalability, since you can also just scale up or down your application instantly. Now, there are also drawbacks, as I indicated before. The library is functional, but should still be considered experimental at this point in time. There are good reasons for Kafka Streams to work with local state stores and changelog topics, such as providing consistency guarantees, resilience, and fault tolerance. Also, exactly once processing semantics through the use of Kafka transactions, which by adding a third-party system like Cassandra to our tech stack and no support for distributed transactions on either side, Kafka or Cassandra, achieving full data consistency on failures or exactly once processing semantics is very challenging, if not impossible. So there's more work to do. And also, for now, there are no window and session stores supported. Which brings us to our next steps. Some of the aligned next steps are to explore buffered and batched writes at the time of when the offsets are committed, which usually takes place in an interval or if it's high throughput earlier. Adding window and session store support, and to address shortcomings on reliability, consistency, and exactly once semantics. Also, I would like to do benchmarks and add an in-memory read cache to boost the performance for read access. The library is open sourced. You can find it on GitHub. It's Apache 2 licensed. So if you want to contribute or provide feedback or simply take it for a ride, please go there. And that takes me to the end of today's talk. So please stay in touch. You can find me on Twitter, GitHub, other social channels, and on my website, thriving.dev. So with that, thanks for attending.